Hey guys, so this is hopefully a quick lesson on 11.3, the normal distribution. And we're going to focus at the beginning of the lesson on what's called the empirical rule, and that is primarily what your e-learning quizzes is about for the spring of 2020. So my PreCalc friends who are watching this, trying to do their e-learning, focus for the most part on the beginning middle part of this lesson. And then everything that kind of follows where we talk about the calculator work is just kind of like bonus information for as you move on into the stats unit of a next class, or maybe if you actually just take a stats class. So today we're going to talk about what's called the normal distribution. And we're going to focus first on what's called the empirical rule, which is a rule of thumb to help us calculate probabilities based on a mean and a certain number of standard deviations off the mean. So the normal distribution is symmetrically shaped, looks like what we refer to as a bell curve. The measure of central tendency goes in the middle. It could technically be a mean, median, or mode, but for what we use it for, we say that it's the population mean, and then we have a population deviation, and then because we say the data is normally distributed, we get to assume it follows this beautiful symmetrical pattern. It's continuous. It like scoots along the x-axis for an asymptotic behavior. So the area under the curve should add up to 100% in theory, but because it doesn't end, it's continuous, it's kind of hard for people to understand like why. And it, numbers, man, they get so tiny that you just don't think about them anymore. So that we just assume in probability that they add up to 100%, which we call a 1. So this next diagram, these are from your textbook. They're showing you what happens when you compare two data sets and you either give a different standard deviation or whether you shift the mean. The mean is a little obvious for people to realize. I did a stupid example of weather temperatures where I talked about like average low temperature and average high temperature in my flip grid last week, or this week, whatever week it was. And like they have clearly different means. So like it doesn't, they didn't quite match up. And that was expected. But if you have the same mean but a different standard deviation, I think that's a good diagram that shows you what happens to the normal distribution and what happens to the data. So this would, if we were doing a traditional test, we would give you a reference sheet that would have the empirical rule. And I'm going to show you what's going on in this empirical rule here. It's a little misleading because, okay, first of all, that's the Greek letter mu. If you haven't run into that, that is a mu. Like kitty kitty mew, but it's spelled M-U. That the symbol kind of looks like a U more than anything else, but it's a Greek letter. The mean is in the middle. And then if you go up one deviation and down one deviation, for the empirical rule, it is said that you have approximately, which we just use it as a calculation, 34% of the data on either side. So that's 68% of the data here, right? And then if you go out two deviations, now you have 95% of the data, which you can interpret as 95% probability that your data occurs within that range. And then three deviations out, like, yeah, that's real good, 99.7% probability. Not quite 100% though, right? So the first thing that I'd like to kind of notate here is after three deviations, which I'll just kind of put a mark here, you have these two teeny tiny tails right here that make up the 0.3% that still hasn't been accounted for. So there is technically 0.15%, you can't read that, 0.15% in these teeny tiny tails, because that would add up to 0.3%. So like a really tiny number, but still, measurable, so we need to include it. So let's talk about that for a minute. If you move in on the deviations, so like this mark right here, this is 95%, right? So I'm going to kind of extend this line here. And I'm going to use a different color so I don't confuse myself. Alright, so from here to here, this red line to this red line, that's 95% of the data, right? So if I think about inside of these lines is 95% of the data, that means 5% falls outside of the data. So, but remember the symmetry here. So if you take that 5% and you break it up, that means you've got 2.5% here and here. Now, you don't see that number 2.5% on the empirical rule here because they've broken it up into chunks, and they took this 2.5% and they took off that teeny tiny 0.15% tail, and that's where that 2.35 came from. Okay, so similarly, if you come into one deviation, that would be from here, I can't draw a line, See how I took this really nice oh boy, took this really nice picture and just ruined it. All right, so in between these two green lines is 68% of the data, which means outside of them we've got 32% of the data. So if you cut that in half, you're looking at 16% on either tail, we call that. Jeez. So, again, I don't see 16 anywhere on this diagram, but that's because this 13.5 came from us taking 16 and then subtracting off this red 2.5. So just the chunk between the red and the green represents 13.5. So here's what I do. Oh, and the 68% is kind of obvious, right? Like cut 68% in half and you got 34 and 34. That's where those come from. Here's what I do on these questions. I've learned after 13 years of teaching that I can't draw, and this is not new. So I finally got smart, and I stole this from the internet, and then I kindly put them on all my slides that I need them for, and I'm just going to kind of, put my own data at the bottom of it, and y'all can just suffer with your horrible diagrams, and hopefully you draw better than I would, because mine are really, really bad. I watched my video from last year, and I was like, oh, maybe I could use this, and then, no, I can't, because they were so bad. All right, so this would be a good thing for you to jot down on your notes. It looks really nice and it's clear, and what we're going to end up doing, and there are shortcuts, but for us, for just this limited exposure, I'm just going to ask you to add up all the chunks that we're talking about. All right, let's see this in action. So this example's from your book, and they've already kindly drawn me something, so that's nice. But we have 880 students, and their heights are normally distributed. It's interesting. With a mean of 67 inches. So you'll notice the first thing that they have is they have the mean of the data in the middle of your normal curve, and then a standard deviation of 2.5 inches. So as they travel 1, 2, how many ever deviations they need to go away from the mean, they just keep adding this 2.5. So that's where the 69.5 came from, and then eventually the 72. And notice they didn't bother looking at the underside of the curve, the left side of the curve, I should say, because they're not interested in anything out there in negative deviation land. So they want to know how many students are more than 72 inches tall. So this probability within this tail here is 2.5%, and I could find that by kind of going to this calculation here. Remember, that was 1, 2 deviations up, and if I just maybe I already knew that was 2.5 because I remembered from my horrible diagram on the last slide, but if you add those up, you get 2.5%. Now, don't be fooled by this question. They don't want percent. They want to know how many students. So out of the 880 students, if you took 2.5%, which isn't that, 0.025, and you multiplied it by 880, that's where they get about 22 students, okay? So again, the empirical rule is just that. It's a rule of thumb. It's kind of an estimation, but it turns out to be really stinking close to the right answer. So it's nice to use. And our quizzes, which is what we're using for your knowledge checker this week, one of them at least, is pretty much empirical rule on all of it. So have that handy when you take your quiz. All right, this example is the same question about those students. They're really interested in those kids' heights, man. And they want to know the probability that they fall between 59.5 and 69.5. So again, remember how the mean was 67? This time they went up 1 deviation and got 69.5 because that was one of the endpoints, but then they backed up 1, 2, 3 deviations. So that's how they ended up landing at 59.5. So I would have gone to this little picture here, and I would have added up all of my little chunks here. And when you do, apparently you get an answer of, right here, 83.85. So I know there's shortcuts, and people who have taken a stats class know all sorts of shortcuts to get those answers. I just think for our limited exposure, let's make this easy on ourselves, okay? So this question here, again, I stole the picture off the internet. You're going to have to draw that yourself. We have the average monthly temperature has a mean of 65. So I'm going to put 65 smack dab in the middle, and then a standard deviation of 5. So every deviation I go up, I'm going to add 5 to that. So 70 and 75 and 80. I like when they're easy deviations to add from or subtract. All right, and then 60 and 55 and then 50. And they want to know the probability that your temperature is between 50 and 70. So here's 50. And here's 70. And again, I know there's probably lots of easy ways to get these answers right. I'm just going to add these all up on my calculator. And I think I already did this one, because actually, fun fact, I already recorded this whole video. My kids were screaming in the background, so I re-recorded it. Alright, so we got 83.85, I believe, on that one. Percent. And this time they weren't trying to trick me with, like, estimate the number of, you know. People who are familiar with stats topics, I know you're, like, itching to use your calculator right now. We're going to do that in this lesson, so just hang tight for a minute. Okay, so this one's about trees. My face is in the way, so let me get my face out of the way. The trees, and there's 200 of them, so keep that in mind for later, has a mean of 120, and then a standard deviation of 16. So to move up the curve, I'm going to have to add 16. So that's like, what, 136 and 152, and I'm going to stop adding because it's getting hard for me. And then I'm going to subtract 16, so that would be 104. Is that 88? Maybe? I think so. Alright, so the first question says, approximately how many trees are more than 136 inches tall? So here's 136, right? So more than that, you can just add up these three chunks, and it ends up being 16%. But remember, we don't want 16% as our answer. We want to know how many of our 200 trees. I should be able to add that, right? Or multiply that. 32. Yeah, it is 32. Yay. Alright, and then what percent, now this one they're not trying to trick you, just what percent lies between 88 and 104? Oh my gosh, that's like a super easy question, because it's this. So I'm just going to write that down, 13.5%. So I really like using the empirical rule. I think it's nice. It really helps if someone already draws it for you. Otherwise, you've got to draw like Mrs. Abruzzo, which is not good. All right, so the next topic is a little, okay, it's not confusing. It's a really simple formula. It's called a z-score. A z-score is used to standardize our data. And I'll talk about originally why we use z-scores, and then I'll talk about why they're still relevant today, even though they feel antiquated. Z-scores take like whatever data you have, and it standardizes it so that it always refers to your curve as having a mean of 0 and a standard deviation of 1 unit. So I'll speak more about this in a minute, but what z-scores are really good for is comparing two sets of data that really have nothing to do with each other. So like, you know, earlier when I referenced my low temperature and high temperature data sets, you know, of course, their means aren't even close to each other, and their standard deviations might seem really off. But in order to compare the two sets of data, if I standardize their data, and I could look at them in terms of a normal distribution that way, it's a little easier to determine like if something was out of the ordinary, I guess. So the z-score calculation is just this. So it says your x value minus your mean divided by your standard deviation. So that seems simple enough. It's just a proportion, right? So what is your z-score? If your x value is 65. So what we're really calculating is how far away you are from the mean, and then divided by how big your steps are, which are your standard deviations. So minus 50. So we're above the mean, right? And then our steps, our standard deviations, are 10. So this comes out to 1.5 as a z-score. So here's a, oh boy, I said I wasn't going to do it. Ugh, it's ugly. Okay. So here's a normal curve with a mean of 0. And, you know, we keep seeing the empirical rule where it talks about like 1 deviation, and then it talks about 2 deviations. And our particular data point of 65 is 1.5 deviations up. So first thing I notice is I couldn't use the empirical rule other than like a sheer estimation, and that wouldn't be good either. But it's in between 1 and 2 deviations, which I kind of already figured out. But here's, well, let me do the next example, and then I'll show you what we used to use z-scores for. All right, so this next one's weird because they give you the z-score. So they tell you it's a negative 0.4, and they want you to figure out the x variable. So your mean is 40, And then your steps, standard deviation steps are 5. All right, so I'm just going to treat this like a little cross product. I'm going to multiply by 5 on both sides. And I'm super going to be able to do that. Let's see, that's a -2 equals x minus 40. And I'm going to add 40 to the other side and get x equals 38. So that kind of makes sense, because if your mean was at 40 and then you were like below it, that means you have a negative z-score, right? So you're not even 1 deviation below it. It makes a lot of sense, okay? Because the deviations are 5. All right, so I'm not going to make you suffer through another picture that I did. Okay, here is why we went through all that. I want you to feel sympathy for me, okay? Back in the day, I was sitting in Mr. Dredge's stats class, and we had to do these, and we, in the back of our textbook, we had a z-table calculation. So you open the back of the book, and then you follow the chart, and you figure out, like, okay, if I have a z-score of -0.42, whatever, and then you follow it down, and you try to figure out what percentage or what probability you were looking at, and it was a pain in the tushy. And then Mr. Dredge showed us, because I'm not that old, guys, we had graphing calculators, okay? So then Mr. Dredge showed us how we could do it on the graphing calculator using a normal CDF and sometimes a normal PDF, depending on your question. And then we were like, well, that's much better. Why'd you show us that? And the reason was, and I was very thankful, because not all questions can be done using the calculation, quick method on the calculator, because sometimes there's a variable within it. Like maybe you don't know a piece of that, so you can't enter it into the calculator. And sometimes they write, especially on AP test, questions where you can't just crank them in the calculator, or better yet, they are on the non-calculator portion of the AP test, so that would stink, right? But for me, when I went to college, I had a professor who wouldn't even let us use the calculator, so I was very happy that Mr. Dredge showed us that way. I'm not going to show you this way, because, there's coronavirus all around, and we have time for that business. If you take a stats class, though, you're totally going to see it, all right? So what we're going to be using today is we're going to be using what's called a normal CDF. And this, if you're on an older calculator, this is the formula that you might want to jot down, because it's the order. But if you're on a newer calculator, it's going to prompt you. So, yay, we don't have to remember anything. We're going to use CDF because it's going to be an accumulation of probabilities where we go from a range. We want to add them all up. Okay. We're going to talk about the value of whether we want to use a z-score or not. Like this particular example is already done for you. So it's showing it by standardizing the data. So here's what's going on. There's 20 airline trips. An employee had a layover of a mean layover of 82 minutes with a standard deviation of 7.5 minutes. So right here is the mean, and then standard deviation of 7.5. And then eventually they want me to find the number of layovers that were less than 75. We'll get to that clue in a minute. So first thing they did is they found the z-score. So x minus mean divided by 7.5, and it came out to -0.93. So if we're thinking, lovely. If we're thinking a z-score of -0.93, that's like almost 1 deviation down. You don't really have to draw this to scale, guys. Clearly I can't draw anything. And they want to know the probability that they were 75 minutes or less. So at this point or lower, they want you to find this probability. Now that's nothing that we can use the empirical rule for unless we were like looking for a real horrible estimation. So what they want us to do now is use our calculator, entering what's called the normal CDF, which is found in your distribution menu, the same place that you found binomial PDF last week. Hopefully you did that work. All right, so we go to second varies, and then there's 2 of them, so be careful. You want normal CDF for the accumulation of all of them. All right, so for lower bound, usually there's like a default in there the first time you reset your calculator. It says like -1E99 or something, which means like a really negative number, So that's fine, because if you remember, what we're asking is like -0.93 and then down. So I'm always a big fan of like -9999 is like I just type a negative and then a bunch of nines. The upper bound, if we were using the z-score, was -0.93, which, if memory serves me correct, that was a truncated rounded value. It's really -0.933333, repeating. But we'll talk about that in a minute. And then if you've already reset your calculator for some reason, your mean already was set up as a 0 and a 1. And what's kind of neat about the older calculators is it always assumes your mean is a 0 and your standard deviation is a 1. But here's where the lazy generation, whatever you are, gets to cheat a little bit. You don't have to remember any of that because it's prompting you here. So then you just hit paste. And then for the older calculators, this is what popped up and you have to remember to type all that in. And then you hit enter. Okay, so let me show you a little secret. Pretend we knew nothing about z-scores. So same question, like scrap all the z-score business. What if I said, well, first I'm going to draw another horrible curve. Okay, cool. And then we got a mean of 82. And we got standard deviations of 7.5. I'll get back to that in a second. And I want to know about them being less than 75. Well, clearly 75 shows up down here somewhere, right? So I want this probability, which regardless of how ugly my picture is, the idea is the same. Okay, so keep in mind what we're doing here. I'm going back to my calculator. I'm going to pull up the normal CDF again. So again, this is like, pretend I didn't even talk about z-scores. So lower bound, just something super negative, like way down there on the curve. So negative 999 works for me. The upper bound was 75 if I never standardized the data. My mean was, I already forgot, I think it was 82. Better check. Yep, 82, and then the standard deviation was 7.5. This was the non-standardized data. This is the raw data. So, look at that. Okay, so I know you're like, oh, it's off. It's not as accurate. No, actually, the first one wasn't accurate because when we standardized the data and we came up with a z-score that we truncated to negative 0.93, that one wasn't really accurate. So potato tomato, guys, because the answer is about 17.5, 17.6%. But think about what's happening here on the question. They want to know how many flights out of his sample of whatever they were, 20 airline trips. So 17.6 or 17.5% of 20 comes out to about 4 flights. And with that being a discrete number, like who cares if it's 4.1, 4.2, 4.3? Like the answer is 4. And really, we're counting air flights out of 20 sample set. Like this is silly. All right, so the point is, you're like, oh, so what way do you want me to do it, Abruzzo? I'm going calculator, non-standardized data. Every single time. The only reason I wouldn't is if my teacher's like, give me a z-score, and then I'll give them a z-score for her. Or if I'm trying to compare two data sets and I'm trying to figure out, like, you know, who's further off from the mean. That would be a nice way to figure it out by calculating z-scores. But I'm not really going to ask you any of that here. So you can thank coronavirus for that, guys. I'm not giving you a thorough stats experience. All right, so at a restaurant, the average time when an order is placed is 12.5. So this right here is your mean. Standard deviation of 1.2. There you go. This is the number of samples, 100 customers. Okay, we'll come back to that in a minute. And they want to know within 14 minutes. So that means 14 minutes or less. All right, so I know it's not an empirical rule question. Get out of the way, face. But I'm still going to write down my data on this curve because I think it helps visualize it. So we got 12.5 here, and then 14 would be, I don't really know how far up, but, you know, let's pretend up here. It's ish. Yeah, that's like my motto in life. So 14 minutes or less, within 14 minutes, right? So they want all this probability. So wherever this is, I don't know, because it's not in the empirical rule, we're going to use our calculator. Non-standard data, though, non-standardized. So I'm going to do normal CDF. And then for lower bound, I'm just going to go super far negative, even though it doesn't make sense. Negative 9999. Big fan of that one, okay? Upper bound is 14. Mean is 12.5. And a standard deviation of 1.2. And when I pop that on the calculator, sorry, I just scraped my speaker. I hope that didn't just make you go crazy. I didn't have it on my calculator. So. All right, so 89.4%, okay? But then they want to know out of 100 random customers, so we'll say about 89 customers were served within 14 minutes. We should answer like humans. All right, so if you calculated and changed that to z-scores, a z-score, excuse me, and then you use normal CDF using the z-score, like, I don't really feel like there's a benefit to you doing it that way for this particular problem. I feel like it's more work, if anything, so I'm not going to do it. This question is very similar. It's about, this one makes me sad because it's about teaching at a college and salary, and that just depresses me right now, so I'm going to skip it. But water temperature, that's fascinating, right? All right, so during 1 October, the average water temperature of a pond was 53. So right there, that's your mean. And then your standard deviation is 2.3. And then this time they want to know how many days is the temperature greater than 50. So here comes another really ugly curve. It's getting good, I know. All right, so here's 53.2, the mean. Greater than 50, I don't know how far because I'm not really like gauging this well, but you know, let's pretend 50 is down here. And I want to know probability of the temperature being greater than 50 this time. So when I do normal CDF, and I'm not going to standardize the data because there's no point. My lower bound this time is a 50, and then even though it makes like 0 sense, I want your upper bound for water temperature to be like 99999, positive this time because you want to go up the curve. That surely is way up the curve, right? Your mean is 53.2, and then your standard deviation is 2.3. Now, once I find my probability, which I totally did, last time I recorded this, I got about 91.8%. So how many days in October? That would be 31 days, right? Do a little song in your head. Yep, October has 31 days. So 31 times 0.918. And again, this is a ish answer. It's about 28 days. Okay. Easy enough, right? So these questions, they're even more boring. Oh my gosh. Doesn't say to do z-scores, so you don't have to, which means I wouldn't. Can't use empirical rule, so you do have to use your calculator in order to answer this one unless you remember how to do z-score tables. I don't. 53 to 59. In this case, when you do normal CDF, this is the first one we've seen like this, so I do want to mark this down. The lower bound and upper bound are those two values. So like the lower bound is 53, and then the upper bound will be 59. So you don't have to do anything weird with like the extreme ends. Ooh, but you do have to be able to write, Mrs. Abruzzo. All right, and then your mean is 56. And then your standard deviation is 4. Now, I didn't type this one in, but I guess I could. That's how much I love you kids. I'll go ahead and type this last one in for you. I miss you all so much. You just want to go back to school. I know, you do too. All right, normal CDF. 53, 59. You know, I joke, but I have a feeling most of you do want to go back to school, especially my seniors. Man, guys, this just stinks. All right, this probability is 0.55-ish. And that's all they want, probability. So, all right, your homework. It's real short. So, it's these practice problems, and I did post the key. 15B says all, but I feel like there's a problem crossed off on it somewhere. I don't know. Just check the key to make sure you don't do any extra work. Once you're finished with this practice work, then you should try to complete the quizzes. We're not releasing the quizzes until it's later on in the week because we want you guys actually doing your practice before you try to throw something down on that quiz. Okay? Do your best. I miss you. Hope you enjoyed the video. Okay, bye.